Okay. Hello, my name is Enrique Preciado, and I'm going to present our final project, Operations Research Final Project, with my teammates Jorge Luis Sánchez Cardosa and Marco Berrocal, case 4-1. First, we're going to start for the basic, which is the LP model. The LP model, or our objective of the LP model, is to maximize the profit. We have, as we can see, we have that four different types of products or different types of constraints: uh, fabric, scrap, demand caps, market minimum, and well, also non-negativity. I didn't include it because I think it's very obvious that everything has to be greater or equal to zero. In fabric, we can see that we have wool, acetate, cashmere, silk, rayon, velvet, and cotton. For wool, we have to have at most 45,000 yards of wool. For acetate, it's at most 28,000 yards. Cashmere, at most 9,000 yards. For silk, 18,000 yards. Rayon, 30,000 yards. Velvet, 20,000 yards. And cotton, 30,000 yards. For also, we have scrap, and we have the demand caps. Demand caps is basically uh, the demand is basically the limit that you can produce, the demand that the market wants you to produce. If you produce more than that, you're going to have waste, and we don't want waste. And the market minimum is the minimum amount that you have to produce for the retail stores. And finally, the non-negativity constraint is the most obvious one. We cannot have a negative number, especially if we're talking about products or merchandise. Let's pass to the next slide. We have right here the optimal solution. As we can see, we have, because this one is a very extensive case, we have a lot of optimal solutions, which are the wool slacks, 44,200, cashmere, 4,000, blouses, 7,000, camisoles, 15,000, skirts, 8,067, blazers, 5,000, miniskirts, 60,000, velvet shirts, 6,000, velvet pants, 0, and cotton sweaters, 0. And our optimal value is 6,008,062,933. And finally, our famous shadow prices, which are acetate, 71.83 dollars, silk $40.33, cotton $67.50, and rayon $17.75. Basically, the shadow prices are the prices that if you add something to one of the solutions, this can alter the price or the value, the final value of the optimal value. Basically, if the shadow price is negative, you're going to subtract that from the optimal value, and if it is positive, you're going to add that to the optimal value.
Uh, so now we have the question if we should drop the velvet shirt since it only contributes $132 dollars in our profit, while its design was of 500,000. So if we are talking about maximizing our profit, this design has been already spent and it shouldn't affect our current decisions. So basically, if each shirt adds us $22 in our margin, and we can sell 6,000, the total amount of profit we can gain is of $132,000. So if we remove it, we lose that amount. And even though it isn't a huge amount of money, taking in consideration the profit we have, it's still a positive number and it's better to have it instead of taking it out. So the best decision would be to keep our velvet shirt in our options. Then we have the scenario if the velvet fabric has no resale value. So this changes the economics of using the velvet. So the velvet costs zeros, and our margin increases because we have the pants that give us $36 and the shirt that give us $18. So in this case, uh, the LP adds 3,667 velvet pants. So our new profit actually increases by 212,000 since now we're gaining 7,074,822.22 dollars.
So now uh, we are at letter D. Why the mix change? Uh, well, this question focuses on how the LP model makes resource trade-offs. Originally, acetate was most valuable when was used in tailored skirts, with a shadow price of the what that is equal to $71.83. But once the velvet becomes free, producing velvet pants give us $18 of profit per yard of acetate. So what do we interpret of that? That's still less than 71.83. But as the model increases pants production, it reduces skirts, and the marginal value of skirts drops while that of pants increases. The LP reallocates acetate until the value of the last yard used in skirts equals the value of the last yard used in pants, about $71.83 in both cases. This equalization is how LP models ensure the most efficient allocation of limited resources. So now for letter E, what happens if blazer labor costs go up by $80 per unit? Well, with that, that drops the net margin of wool blazers from 155 to $75. As a result, the model cuts blazer production to the minimum of 3,000 units, just enough to fulfill commitments. Resources that were previously allocated to blazers now go to other sections with better margins, like skirts or camisoles. Uh, this change reduces total profit from 6.86 million to 6.53 million, a decline of a total of 300,033. It highlights how sensitive our model can be and how sensitive our model is to cost changes and why labor negotiations are strategically very important.
Okay, so why do we need 10,000 yards of extra acetate? Why we should do or take that decision or that into consideration? Well, as I mentioned earlier, remember the shadow prices. Acetate has a shadow price of $71.83. Basically, as we can see here, the shadow price of the acetate, which is $71.83, multiplies by the 10,000 yards that we are giving or that we are buying. So basically, this means that if we multiply that value, it gives us the number of $718,000 or 718K. Basically, if we remember what I mentioned, this shadow price it's positive So it will affect, well, all the shadow prices affect the final value, no, or the optimal value. But in this case, as we can see, the shadow price is positive. Well, in this case, all the shadow prices are positive. So if so basically if we multiply uh, if we make that multiplication, it's going to give us a positive number, 718K or 700,000, well, $718,000. So we are going to add that quantity that we added up to the optimal value. Basically, it gives us 7.58 million dollars, or 7,581,266.67 million dollars, if we want to be more precise. So yeah, uh, basically, I think it's a great decision to buy 10,000 yards of extra acetate, because as we can see, our final profit goes up instead of going down.
So now for the final subsection, we have the November clearance. So for this, we have to imagine that we allow to sell the unsold inventory at a 60% of discount of the original price. So with this amount of discounts, most items become basically unprofitable. So we cannot make any money out of them. But there's an exception, which is the cashmere sweaters, which for each of them that we sold, it would give us around $3 of profit. So as a result, the model produces an additional 2,000 cashmere sweaters, and then it sells them in November, raising a profit to 6.93 million, or to be more exact, of $6,922,933. So this scenario shows that clearance sales are useful, but only for specific high margin items. So dumping everything at a discount basically wouldn't work, and it will only lower your profits.
So, for the final slide, certain recommendations. Uh, so, finally, to wrap it up, here are the four major insights that we think from our analysis. Keep positive margin items, revisit Blazer's labor or promises, prioritize asset day purchases, and use clearance only for high margin goods. So, one, keep producing any item with a positive margin and don't letting some cost like past design investments or another judgment. Then also watch for rising labor costs, uh, especially for items like blazers. These shifts can reduce your flexibility and also lower your profit. For the number three, acetate is the most valuable material in the model. If more can be sourced at a reasonable cost, so we must do it. So because the return is worth it. And finally, number four, use clearance sales only for items that remain profitable, even at a discount. In our case, that meant only the cashmere sweaters. So overall, the linear programming helped us to explore these what if scenarios and clearly make better these data business decisions. So thank you for your attention.
Thank you.
Thank you.